Let's get started on today's notes over linear and quadratic systems of equations. There are three types of solutions that we're going to talk about with linear and quadratic systems. So a linear and quadratic system is one where you have one equation that is linear and one equation that is quadratic. So obviously on these three graphs that we're given, we have a straight line and we have a parabola, right? The straight line is the linear equation graphed and the parabola is the quadratic equation graphed. So when we look at this first type of solution, you have a parabola that's graphed, and I'll zoom in here. You have a parabola that's graphed and you have a linear or a line that's graphed, and you can see that there are 2 points of intersection between that line and that parabola. So this is a type of situation where you'll have two solutions. In the second type of solution, you can see that the line next to the parabola is just tangent to that parabola, meaning it will only intersect that parabola once. So in that type of situation, you will have one solution. And then you could have a solution where, or a type of solution where you have zero solutions, meaning there's no intersection at all, right? So this blue line that's graphed doesn't intersect that parabola at all. So those are the three types of solutions that you would encounter. So how do you solve a system of equations that has one linear equation and one quadratic equation? Well, one of the methods you can use is you can graph it and just find the points of intersection. So in this first example, you can see that our parabola is written in vertex form. So we can easily find the vertex and from there graph it. And then our line is written in slope-intercept form. So let's graph each of these. The first one I'm going to graph is the quadratic. So x minus 4 squared plus 2, I know using quadratic transformations that my vertex is going to move right 4 and up 2. So starting from my origin, I'm going to go right 4 units, up 2 units, and that's my vertex of my parabola. I know there's no stretch or compression, so it's just going to take that basic the pattern where from my vertex I go out 1 and up 1 on both sides, right? Out 2, up 4, and out 3, up 9. But we're just going to go up that many because that's how we can graph it here. And if I wanted to, I could go, out 1 more and up right there, right? So I could do that. All right, so there's what my quadratic looks like when I've graphed it. Let's now look at this line. Y equals 2x minus 3. I know when I'm graphing lines, I graph my y-intercept first, which is negative 3. So 1, 2, 3. And then my slope is positive 2. That's just 2 over 1. So I'm going to go up 2 over 1. And I'm just going to keep doing that. And I can already see that point of intersection. Up 2 over 1, up 2 over 1, up 2. Oh, and I'm really glad I went off of my graph and graphed it because as you can see, there is one of the points of intersection. So what are these points of intersection? Those points of intersection are my solutions. So what are those points? Well, this one right here is at right 3, up 3. So that's going to be a solution, right? Because your solution is your point of intersection, right? So here we have 2 points of intersection. We're going to have 2 solutions. And then this point up here, if you want to find that point, it's right 7, up 11. So 7, 11. So my solutions in example number 1 are 3, 3 and 7, 11. So you can solve by graphing. I like to use the graphing method, A, when I have a graph handy, and B, whenever I have my quadratic written in vertex form. That's really easy to graph. If you think it's really easy to graph. If not, then you might want to use this next method, which is another highly popular method. You can solve it algebraically using the substitution method. Sometimes solutions are difficult to find graphically. We don't always have those pretty nice integer solutions in Algebra 2. So algebraically, we can use the substitution method to solve a system of equations. The steps that you're going to use to solve, and I know it's kind of like difficult to even picture it whenever we're just going through the steps, but these are definitely what you can refer to as we work through a problem. The first thing you're going to do is isolate one of the variables in one equation. That means get y equals or x equals all by itself, right? And the second step is to substitute this expression into the other equation for the variable. This should result in a quadratic equation. Then you'll solve the quadratic for the x values. You can do that if you have a quadratic equation. You can solve by factoring using the quadratic formula, completing the square, to determine the x values of the solution. Once you have x values, you can substitute the x values into either of the equations to solve for the remaining y values. So again, this is what you can refer to as we're going through example number 2. This says solve the following systems of equations using the substitution method. Round all decimals to the nearest thousandth. So in this problem, we are given a quadratic equation in standard form, and we're given a linear equation. But what I want to do is put this linear equation in slope-intercept form. How do I do that? I can add 7 to both sides. So this linear equation would actually look like this, 2x plus 7 in slope-intercept form. The next thing that I'm going to do, as you can see, I've got y equals in this quadratic equation and y equals in this linear equation. What I'm going to do is I'm going to take this 2x plus 7 and substitute it in for y in that first equation, right? Because if y equals 2x plus 7, anywhere I see y, I can replace it with 2x plus 7. So here's what it looks like. And this is step number 2. 2x plus 7, instead of y equals 2x squared plus 12x plus 16, 2x plus 7 equals 2x squared plus 12x plus 16. So what do we want to do, right? We're going to set this is going to be a quadratic, and we're going to set it equal to 0. How do I do that? I'm going to subtract 2x and subtract 7 from both sides, and subtract 7. When we do that, we get 0 equals 2x squared plus 10x plus 9. And in this situation, what I am going to do is use the quadratic formula to solve, because this is actually not factorable. So that's I can't solve this by factoring because it's not factorable, right? I'm thinking 2 times 9 is 18. What two numbers would multiply to 18 and also add to 10? Well, there are none, right? So, I mean, I've got 6 and 3, 9 and 2. None of those add to 10. So what I'm going to do is use the quadratic formula. And that is going to look like this. I know A is 2, B is 10, and C is 9. So I'm going to plug this into the quadratic formula, and you'll have to forgive me because I'm going to sing it as I do it, right? So x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And there we go. I've got all of my values entered in the quadratic formula. And now we're going to go up here and we're going to solve this quadratic using the quadratic formula one step at a time. So what I like to do first is simplify the discriminant, right? That's that portion that's underneath the radical, right? That's my radicand. So this 10 squared, 100, minus 4 times 2, which is 8, times 9, which is 72. 100 minus 72 is 28. So I'm going to rewrite it as x equals negative 10 plus or minus the square root of 28 divided by 2 times 2 is 4. So we're just doing one step at a time. So what I want you to do now, and you should have already, watched the lesson over solving using the quadratic formula. Okay, I'll put a little card in the upper right-hand corner. If you need help solving using the quadratic formula, that'll be up there in the upper right-hand corner. Just click that to give yourself a little refresher over solving using the quadratic formula, because what you're going to do is you're going to set two equations. X equals -10 plus the square root of 28 over 4, or x equals -10 minus the square root of 28 over 4. So go ahead and pause the video, use your calculator, do that now, and we're going to take the decimal answers, and you're going to round to the nearest thousandth. So that's 3 decimal places out. And you should have gotten, since we're rounding, I'm going to use this little x as approximately -3.823, -3.823, and -1.177. So those are the x values of the solution to the system. So what do I need to do to find the y values? Well, this is my fourth step. I can plug in those x values into any of these equations, into this first equation, this second equation, or this new equation that I manipulated from that linear equation, and I can find the y values. Well, I'm going to use this one right here, right? This y equals 2x plus 7. So I'm going to use y equals 2x plus 7. I'm going to substitute this -1.177 in there. So y equals 2 times -1.177 plus 7. And you can use your calculator to do this, or not, and pause the video and off, on some scratch paper, -1.177 times 2, then add 7 to that, and you should get y equals 4.646. And then I'm also going to do y equals 2x plus 7, and I'm going to substitute -3.823 in for x. And again, we'll do the same thing. I'm going to use my calculator and plug it in, and I'm going to get y equals -0.646. So I have the x values and the y values of the solutions. So let's write our solutions as ordered pairs. The solutions in this case are, let's see, in this first one, let's see. I'll do this one first, right there. So I've got -3.823 comma -0.646. That's one solution. And let's do this other one, -1.177 and 4.646. That is the other solution. So that is how you could find this solution to the system of equations algebraically. Let's move on to example number 3. In example number 3, let's see, what do we have here? Okay, I've got y equals 0.5x squared plus 6x plus 16. So I've got a quadratic written in standard form, and then I have a linear equation not written in standard form. So what I want to do is actually solve for y in this equation. Okay, I'm going to do that by subtracting 2x. So I'm going to get -y equals -2x minus 8. And then I don't want what -y equals. I want what y equals. So y equals +2x plus 8. So I have this equation, this linear equation written in slope-intercept form. My second step, if y equals 2x plus 8, anywhere I see y, right there, I can replace it with 2x plus 8. So instead of y equals 0.5x squared plus 6x plus 16, I'm going to write 2x plus 8 equals 0.5x squared plus 6x plus 16. And we're going to do the same thing that we did in problem number 2. I'm going to subtract 2x and subtract 8 from both sides. And I get 0 equals 0.5x squared. We did that 6x minus 2x is 4x. And then 16 minus 8 is +8. In this example, what I'm going to do is factor it, right? I can factor this. So how am I going to do that? I use the slide and divide method, where I'm going to do 0.5 multiply, I'm going to multiply that by 8. So I'm going to get 0 equals x squared plus 4x plus 4. And then I need two numbers that multiply to 4 and add to 4, and those are 2. So x plus 2 times x plus 2. And then at this point, this is what a lot of students forget, this 0.5 that I multiplied into the last term, I need to divide out of the last term. And when you do that, 2 divided by 0.5, or 1/2, simplifies to 4. X plus 4 times x plus 4 is just x plus 4 squared. So I factored it. So I've got x plus 4 squared. And in this case, what's really nice is I love these ones that you can factor. It's so easy. And if you take AP Calculus, almost everything is factorable. So you need to be really good at factoring. In this case, if I were to solve for x, I take that factor, that x plus 4, and I set it equal to 0, and I get x equals -4. So in this case, I have one solution, and I know the x value of that solution is -4. So at this point, now I need to determine the y value of this solution. So this portion right here where we solved it, that was step number 3. I'm going to go over here to step number 4. I'm going to take this -4 and plug it into any equation, and I'm going to solve for y. Which one would you like to use? I think this equation would be easiest. Y equals 2x plus 8. Y equals 2 times -4 plus 8. In this case, what is y? 2 times -4 is -8. -8 plus 8 is 0. So my solution in this case, I have one solution, one point of intersection if you were to graph it, and that solution is -4, 0. So we didn't graph it. We solved it algebraically, that point of intersection. What is the x and y value that these two equations share? But if I were to take these and use my calculator and graph this first equation, quadratic equation in standard form, and this linear equation in standard form, and find that point of intersection, which I will show you how to do, that is what you would get, the point -4, 0. Let's move on to our next example. I know these are long notes, but each of them kind of has, right, we had an example that had 2 solutions graphically, an example that had 1 solution, or 2 solutions algebraically, 1 solution algebraically. And this one is another example. What kind of example do you think it's going to be? Well, we're going to solve it using all the same steps. I've got a quadratic equation. It's written in standard form. And I've got a linear equation, not written in slope-intercept form. I'm going to solve for y. So in this first equation, how would I solve for y, this linear equation? I would add x to both sides. So I got y equals x plus 10. So now I have two equations written in y equals, right? Y equals form. What I'm going to do is if y equals x plus 10, anywhere I see y, I can replace it with x plus 10 because they equal the same thing, right? They represent the same amount. So I can use substitution. X plus 10 equals -x squared minus 8x minus 11. And now I'm going to set this quadratic equal to 0, and I'm going to solve. So 0 equals, I'm going to subtract x from both sides and subtract 10 from both sides, and I get -x squared minus 9x minus 21. And then I think about, are there two numbers that would multiply to -21 that have a sum of -9, and there aren't. So I'm going to, in this case, use the quadratic formula. That is kind of my go-to. You could obviously try to complete the square, stuff like that, but I tend to, my go-to, if I can't factor it, is the quadratic formula. So that's what I'm going to do. So it's already written in standard form. I know A is -1, B is -9, and C is -21. So I'm going to plug this into my quadratic formula. X equals the opposite of B plus or minus the square root of B squared minus 4AC. A little slow at that point, all over 2A. Okay, so now I've got all of these values written into my quadratic formula, replaced all the variables in there with their respective values, and I'm going to simplify that discriminant first. This discriminant, -9 squared, well, that's 81. then negative 4 times negative 1 is positive 4. Positive 4 times negative 21 is negative 84, so minus 84, divided by negative 2, and I get x equals 9 plus or minus 81 minus 84 is negative 3 over negative 2. And in this particular case, we have a negative value as the discriminant right here, right? So what does that mean when you have a negative value as the discriminant? It means your solutions are imaginary, right? They're not real, which means in this case, do I have any real points of intersection? I do not. So this is one of those examples where the discriminant is negative. Therefore, fancy schmancy, therefore, there are 0 solutions to this system. So algebraically, this is the type of situation you would encounter when you have 0 solutions, 0 points of intersection. If you were to take these two quadratics and graph them on a coordinate plane, they would not intersect. So this is that third type of solution that you might see. And then obviously with all of this, solving this linear and quadratic systems, we're going to look at the systems application. And what I always encourage my students to do whenever you're given a word problem, I've taught 6th grade math all the way up to high school pre-calculus at this point. And what I would encourage you to do is to draw a picture, because sometimes we struggle with just the words. Let's visualize it. Okay, so I'm going to read this. A cannonball is shot at the base of a hill upwards toward the top of the hill. The path of the cannonball can be modeled using the equation h equals negative 0.004 d squared plus 0.14 d plus 1. The slope of the hill can be modeled using the equation h equals 0.2 d. Where will the cannonball land? I've got two equations here. The first equation is h equals negative 0.004 d squared plus 0.14 d plus 1. My second equation is h equals 0.2 d. What I'm going to do is, this is the same type of situation right here as what we just encountered, right? I've got one equation that's in standard form, it's a quadratic. One equation that would be in slope-intercept form that is linear. We've just got different variables, but it's all in the same form, right? Instead of y, we have h. Instead of x, we have d. If you feel more comfortable using the x and y values, then replace them. What I'm going to do is use the same process to solve. I've got 0.2 d equal to h. Anywhere I see h, I can replace it with 0.2 d. I see h right there. So h equals, instead of h equals all of that, I've got 0.2 d equals negative 0.004 d squared plus 0.14 d plus 1. And maybe I should go ahead and draw my little picture here, because I didn't do that yet. So let me actually take this opportunity to draw a picture. If I have a cannonball is shot at the base of a hill, upwards toward the top of the hill, then I've got a hill right here. I have a cannon with a cannonball in it. And this hill right here, the slope of the hill can be modeled using the equation h equals 0.2 d. And then the path of the cannonball, which means this cannonball has been shot, and it's going to go and it's going to land somewhere. The path of that cannonball is this right here. Okay, so what we're finding here is this point of intersection. Where will it land given the path of this cannonball on this hill? That's what we're finding. And I probably should have drawn this picture first for you to get kind of a visual of what we're looking for here. But there's our visual. We're finding a point of intersection. We're going to find it algebraically. So what I want to do now, and I'm going to change colors here, is I'm going to set this quadratic equal to 0. And I'm going to do that by subtracting 0.2d from both sides, minus 0.2d. And I'm going to get 0 equals negative 0.004d squared minus, is that going to be, that sure is 0.2, and then it really minus 0.14, that's 0.06 minus 0.06 d plus 1. In this situation, I've got some decimals here, and I don't really like working with decimals. I would rather be working with integers, right? Those positive or negative whole numbers. How can I do that? I can multiply this entire equation by what would get rid of this smallest decimal right here. That is negative 4 thousandths. If I want to get rid of that, that looks like this, negative 4 over 1,000. How would I get rid of that? I'd multiply it by that denominator. So if I multiply this entire equation, every single term gets multiplied by 1,000, that'll get rid of all of my decimals. So I should get 0 equals negative 4d squared minus 60d plus 1,000. And I'm going to factor this. And really what I could have done is divided out of 2 and done that, but I didn't do that yet. And I should have done that, but I'm going off what I've already done here, and so I'm just going to stick with that. So I'm going to solve using the slide and divide method, where I multiply this negative 4 into my last term. So I get d squared minus 60d. Negative 4 times 1,000 is negative 4,000. I'm looking for two numbers that have a product of negative 4,000 and a sum of negative 60. If you had divided out a 2 as a GCF first, which is really what you should do, then you know, you'd be working with smaller numbers here. But we're going to end up getting the same thing, so we're going to be fine. So two numbers that multiply to negative 4,000 that have a sum of negative 60 are negative 100 and positive 40. So 0 equals d minus 100 times d plus 40. When I solve those, or I'm sorry, at this point, because I multiplied this negative 4 into my last term, I need to divide it out of that last term. So my factors are actually 0 equals d plus 25 times d minus 10. When I solve for these solutions, these x values, but we'll call them d values, I'll get x equals, I set each factor equal to 0. I keep writing x equals, d equals, like I said, I'm used to working with x and y. So d equals negative 25 and positive 10. So at this point, what do those d values represent? They represent the distance, right? So can we have a negative distance? No, we have a negative 25 as a distance. That would be considered an extraneous solution. Given this particular problem, this situation, this doesn't make sense, which means my solution is 10. I only have one solution right here, that point of intersection. The distance is 10. What's the height up the hill? I can take that d value and plug it into any equation. I'm going to plug it into that one right there. H equals 0.2 times d, which means h equals 0.2 times 10, which means the height is 10. So your solution for this particular problem, there's only one solution, and that's 10, 2. For this system, right? For this system of equations in this situation. So how might I write this? The distance is 10 units, and the height is 2 units. We don't know what units we're talking about, so we're just going to write units there. And that concludes your notes over solving a system of equations where one equation is linear, one equation is quadratic. I hope it was helpful.